I took the formula from the textbook, and I believe you all learned this in statics and strength of material, that the factor of safety is equal to the ultimate strength divided by allowable. Okay. Now, if you look at the stress strain curve and the magnitude of structure ASTM A36, we know that we have a yield strength of 250 and you have an ultimate strength of 400. Okay. If we were to use this formula, means the material is behaving in what region? Plastic region. So this formula is not wrong, but it has to be treated with caution. So what do I mean? Okay. So what do I mean by it has to be treated with caution? So for ductile material, so ductile for this case, where the yield strength is a lot smaller than the ultimate strength, okay, the factor of safety should be the yield strength divided by stress allowable. Now we might say that, Eugene, then the textbook is wrong. Not necessary. Okay? That formula provided by the textbook is also partially correct. So when is it correct? For brittle material, okay, where the yield strength is approximately equal to the ultimate strength. Okay, brittle material don't have ductility at all, right? It cannot work in a plastic region. Okay, so this is for ductile material. For brittle material, it behaves like this. Okay, where this is the stress yield and this is the stress ultimate strength. So this is for brittle material. Right? So when it's brittle material, the yield and the ultimate strength, they are about the same. So when that's the case, then you can use factor of safety is equal to stress ultimate strength divided by stress allowable. Okay. So as an engineer with a degree, you have to know when to apply what. Okay. As I say, the textbook is fine. Okay. For ductile material, you use yield strength divided by factor of safety is equal to U divided by allowable. For brittle material, is the ultimate strength divided by allowable. Okay. Now, coming back to the material handbook, okay, you can see that the material is either tested in tension, okay, and very limited shear, okay, and compression is usually for brittle material because brittle material can only withstand compressive stress, not tensile. Okay. But what are these stresses? You know it's yield strength, you know it's ultimate strength, but how do they get those data? Okay. So let's focus on tension. Okay, let's focus on tension. So in tension, right? So what they test in tension is in unidirectional. Uni means one direction. So if this is our specimen, right? So if there's our specimen, this is our X, that is our Y, and over here, this is our Z, right? And then if we have our element over here, what they test out is they test it out in uniaxial tensor. Right? So this looks familiar. This looks like our what? Our chalk. Okay. So when that's the case, when we draw our element, right? When we sketch our element now, if you look at our element, and then we start to draw this, right? So our element has stress X. Y is equal to 0. There's no stress, right? So when we label this as our X and I label this as our Y, okay, then when we draw our Mohr circle, okay, so this is our Mohr circle, right? So this is our normal stress, shearing stress, element rotate clockwise, anti-clockwise. And we know that this over here is our stress Y line. And then over here, right over here is our stress X line. And then we label this as our point X. And we label this as our point Y. Now we can construct a circle. Okay, so now we can construct a circle. Okay, so what we see over here, X, which is our stress X over here, right? This is also our stress one value. Okay, so what I'm trying to tell you is this. Over here, this over here, okay, not in the plastic region, only in this state, this is our principal stress. Okay, what we measure is the principal stress, and I've proven to you down here. Okay, this is our principal stress. Are we clear? Right. So when we test our material under unidirectional, it can be tension, it can be compression. Okay, we are measuring the principal stress. Okay, so all the material handbooks that you will see, okay, like tables like this, okay, for the yield strength, it is our what? Principal stresses. Are we clear? Okay. So whatever we see from handbook is principal stress. Okay. So the next thing that I want to focus now is we want to look at shear. Okay. Let's look at shear. So next we are going to look at shearing stress. Oh, before I go on, right? This normal stress that we get, right? It comes from a formula, a load formula that looks like this. Okay, so Px over A plus minus Mz over Izz multiplied by Y plus minus My over Iyy multiplied by Z. Okay, in case some of you, hey, this is based on combined loading. So combined loading over here, this is your axial load. And over here, this is due to bending moment. Okay. After term test 2, we will go into, no, before term test 2, we'll go into more detail to this aspect. Okay. Now, the next thing that we are going to look at is we are going to look into shearing stress. Okay. So shearing stress are stresses acting parallel to the surface. Okay. Acting parallel to the surface. Yeah. So in shear, so let's look at shearing stress first. Okay. So this is X and this is Y. Okay. So I'm going to draw an element. Okay. And this element over here, the shearing stress looks like this. Okay. And this arrow over here is known as our shear X, Y. Okay. Now, why is that known as shear XY? Okay. What's that? The first, so tau over here means is shear. X over here is the intersecting plane. Okay. Y down here is the direction of the shear stress. Okay. Watch this. Okay. Over here, when I'm highlighting in yellow, as you can see, that is the plane. If I draw that plane onto my transformation over here, it intersects the x-axis. Okay, so that is why you have the first x. The y is the direction. Shear stress direction. Okay, so this over here up is related. Okay, is related. Hold on. Okay, so this is related to the shearing stress direction. So the other arrow over here, this is known as shear. The intersecting plane is y. The direction of the shear stress is x. Okay. So what do you see down here? This configuration is known as positive shear. Okay. That is known as positive shear. And in positive shear, okay, I'm going to draw the deformation pattern. The deformation pattern looks like this. Okay, the deformation pattern look like this. And some of you say, hey, that is a bit confusing. Why is that? Okay, why positive shear, the deformation looks like this? Okay, so now I'm going to turn on my camera again. Okay, so you can see my paper again. And I'm going to